All right, everybody. We are back with a video on function operations and domain. So what we're going to talk about first is domain. Now, domain is a pretty simple concept that people have trouble with because you just kind of have to switch your mind a little bit. The best way to think about domain is to think about what values of x cannot happen. But then you just go write it in a way that you're just saying what x is allowed to be. Okay? So let's take the first one for example. F of x is equal to x. Do you have any restrictions on x? None. So x can equal all real numbers. There's no restrictions on x. Okay? Now the second one, x squared. So think about it in terms of positives, negatives, and 0. Can you square a negative? Yes. Can you square a positive? Yes. Can you square 0? Yes. So this second example, x can equal all real numbers. Now the next one. Can you divide 2 by a positive number? Yes. Can you divide 2 by 0? No. Can you divide 2 by a negative number? Yes. So for this one, x can equal all real numbers except x cannot equal 0. Okay? So that's kind of what you're thinking about. Now, you could also just say x cannot equal 0. Depending on what you're being asked, a lot of times you have to state what it's allowed to be and what it's not allowed to be. So you'll see in this next example right here. So x, is it allowed to be a negative number? No, because you cannot take the even root of a negative. Can it be 0? Yes. Can it be positive? Yes. So this is x is greater than or equal to 0. Okay, so you don't want to say x is not allowed to equal negatives. You want to state it in a way that you're listing what x is allowed to be. So x has to be greater than or equal to 0. Next one, cube root of x. You are allowed to take a cube root of a negative, a positive, and 0. So there are no restrictions. So x can equal all real numbers. That's your domain. This one. Now you are squaring something, and then you're going to take the fifth root. Now the fifth root is an odd root. And you can, as we just saw in the last example, we can take the odd root of anything. So this is x is equal to all real numbers again. But the fourth root is an even root. And as we saw earlier, even roots, you cannot take the even root of a negative number. So this would be like saying x has to be greater than or equal to 0 again, because you could not take the fourth root of a negative number. So if x was negative 3, you would have negative 3 cubed, which would be negative 27, and the fourth root of a negative 27 would be not possible. So in this example, since it's an even root, you can never take the even root of a negative number. So x has to be greater than or equal to 0. And finally, remember, a negative 1 power just means reciprocal. So that's just another way of saying that f of x is equal to 1 over x, which means you cannot divide by 0 again. So x is equal to all real numbers except 0. Okay? Now, I just want you to know that everything that we just did there were just like parent functions. There was nothing fancy happening. It was just your basic rules for domain. So this next section, you're going to be finding the domain of all of these functions. Now, if you know the functions from right above, the parent functions, what you have right below is the same thing. You just have to tweak it a little bit. Okay? So why don't you pause the video and see if you can think about what the domain is for all of these functions. And then as soon as you're ready, click play, and we'll see how you did. So this first example, as we saw earlier, you can square anything. So there are no restrictions on this. So x can be equal to all real numbers. Now we learned that the square root can never have a negative on the inside. So the key word is on the inside. So that means x plus 3 has to be greater than or equal to 0. So that means x has to be greater than or equal to a negative 3. So a negative 3 plus 3 would be 0. Negative 1 plus 3 would be 2. If you had a negative 4 plus 3, that would be a negative 1, and now you're taking the square root of a negative. That's why it's got to be greater than or equal to a negative 3. So if you just said x has to be greater than or equal to 0, you were on the right track. However, you have to be very specific to this example. The inside of an even root has to be 0 or a positive number. You can never divide by 0. So x minus 2 is your denominator. So if you said x cannot equal 0, that would be incorrect because 0 minus 2 is a negative 2, and 2 divided by a negative 2 is just a negative 1. You can't divide by 0, which means x is equal to all real numbers except 2. And you can just set the denominator equal to 0, kind of like what we did in our rational functions unit, where you just set the denominator equal to 0, and that was your vertical asymptote, and it was also what your domain was not allowed to be. X was not allowed to equal 2 back then. So, same thing. X is equal to all real numbers except 2. Cube roots. We know there are no restrictions on cube roots, so x can equal all real numbers. We are taking the square root because that's what's in our denominator. So since this is an even root, and there's nothing fancy inside with this, it's just the square root of x, cubed of course. This is just another example of x has to be greater than or equal to 0. And finally, the last one is the trickiest one of all, because you have a 1/2 power, which is a square root, so this is a square root in the denominator, but we also can't have 0 in the denominator. So we have to think about it in both ways. So you can't have the square root of a negative, and you also cannot have a 0 in the denominator. So that means this x plus 3 has to be greater than 0, not greater than or equal to. It has to be greater than 0. So in this example, you would just set x plus 3 has to be greater than 0, which means x has to be greater than a negative 3. Okay, so remember, in this last example right here, I kept them the same. So you can see the only difference is you can take the square root of a 0. You cannot divide by 0. That's why this one is x is greater than a negative 3. Okay, so that was a lot to talk about. Domain is a pretty big topic, so this video is going to be quite lengthy because we still have a lot more to talk about. So now we're going to talk about performing operations or compositions, and then we're going to state the domain. So that's why we had to talk about domain first. But this part's actually really not that bad. F of x is 2x minus 3, and g of x is x squared plus 5. So if this just tells us to do g of x minus f of x, that's all we're going to do. But we're also going to state the domain. So a really important detail when you do that is to start off by listing your domain for each function. So this is just 2x minus 3, so x can equal all real numbers. And we can square anything, so in this one, x can also equal all real numbers. So now let's just start doing what it asks us to do. So g of x minus f of x. So that's x squared plus 5 minus, and then f of x is 2x minus 3. You do not have to write it in parentheses, but sometimes you'll find it helpful for an example like this. This is going to turn into minus a negative. So your answer is just going to be x squared, and then you have minus 2x, and then you have 5 minus a negative 3, which is just going to give you 8. And x squared, x, they have no restrictions. So the domain of g of x minus f of x is also x equals all real numbers. Okay, sometimes that's going to change. Like this next example. We have g of x over f of x. So that would be x squared plus 5 over 2x minus 3. But as we talked about a little bit ago, you cannot divide by 0. So you have to set your denominator equal to 0. And that's what x is not allowed to be. So add 3 to both sides, divide by 2. X can equal all real numbers except 3/2. Okay, so 3/2 is not allowed to be x. F of x times g of x. That's just foiling. So we're just going to take 2x minus 3 and multiply it to x squared plus 5. And that's going to give you 2x cubed minus 3x squared plus 10x minus 15. There are no restrictions on anything here, so x can equal all real numbers. Okay, so that is just performing operations. The next row is compositions. A composition means you're going to take a function and substitute it into another function. So this means that f of x is going to have g of x substituted into it. So the one that's inside is going to go inside of the other one. So we have f of x, which is 2 times x minus, or 2 times x and then minus 3. But g of x is going to be substituted into the x. So we have 2, and there's our x, minus 3. Now g of x is going to be substituted into it. So g of x is going into f. So where our x would be, we're going to substitute x squared plus 5. And now you just simplify. So you have distribute 2x squared plus 10 minus 3. You have 2x squared plus 7. And of course, there's no restrictions. But one thing you always have to check is what's being plugged in. So g of x has all real numbers, so there's no restrictions on this guy. So x can equal all real numbers. The next example is when you're going backwards. So now f of x is going to be substituted into g. So where you have an x, you just put parentheses, and then you finish writing. So we have x squared plus 5, and you substitute f of x into the x of g. So you have 2x minus 3. Okay, so that's what you're doing. The f goes into the g. So 2x minus 3 goes into the x, and now you just square it. So you have 4x squared minus 12x plus 9 plus 5. So you have 4x squared minus 12x plus 14. And one last time, x is allowed to equal all real numbers because you can square anything. Okay, so that was a pretty easy example. But that covers your function operations, which are just adding, subtracting, multiplying, and dividing. And it also covers compositions, when you insert a function into another function. That's called composition of functions. So we can do that again, but this time we're going to get a little bit more challenging. Okay? I have no idea why I have that all written twice. So we're going to do this again. But now we're going to take it up a little level and make things a little bit more complicated. Again, for domain purposes, this is a square root. So for this guy, x has to be greater than or equal to 0. This is an odd root, so he's fine. He's allowed to be all real numbers. And for this one, this is, remember, a negative exponent means you're going into the denominator. So this is 6 over x squared. And a denominator is never allowed to equal 0. So for this guy, x cannot equal 0. So you have to keep that in mind whenever you're working with these. So we have m of x times n of x. Now right off the bat, m would never be allowed to be a negative number. So that follows. But now we're just going to do m of x times n of x. So that's just 2x to the 1/2 times 4x to the 2/5. 2 times 4 is 8. And x, when we multiply, remember we add our exponents. So that's going to have to end up giving us 5, 4, 9 tenths. Okay? And then you just have to rewrite this as a radical. So we have 8 tenth root of x to the 9th power. And now that guy is done. However, we need to state the domain. This, again, is an even root. And an even root is not allowed to be a negative number. So x has to be greater than or equal to 0. Okay? Next example. We have m of x divided by n of x. So m of x is 2x to the 1/2 divided by 4x to the 2/5. And then you would just have to simplify. So 2 over 4 is equal to 1/2. And you have 1/2, which is bigger than 2/5. So you would subtract this time. And 5 tenths minus 4 tenths would be 1/10. So this is x to the 1/10 over 2. So your final answer would just be the 10th root of x over 2. And again, this is an even root, so x has to be greater than or equal to 0. Last two problems coming. We have n of m of x. Now this is something that I kind of talked about earlier. What you're inserting, we have to have that domain follow. So this is x is greater than or equal to 0. That's going to follow this. So m is going to go into n. So we have 4, and then we have our x raised to the 2/5 power. And then we're going to substitute m in there, which is 2x to the 1/2. And then we need to work this all out. So we have to first raise both terms on the inside to 2/5 power. So that's going to be the 5th root of 4 times, and then 1/2 raised to the 2/5 power. When you raise, you actually multiply. So that's going to give you x to the 2/10, which is 1/5, which is just the 5th root. So this is the 5th root of 4x. And then don't forget about your 4 in front. So we have 4 times the 5th root of 4x. Now I know you're allowed to take the 5th root of anything. However, the domain that goes must follow. So even though there's no restrictions on this, because it's an odd root, x still has to be greater than or equal to 0. Okay? So that's the tricky thing that I wanted to make sure I pointed out. And finally, the last one, n of x. That's all real numbers, so what's going inside is fine. But since we're going to have a division here probably, because n is going into t. So t is 6. And then we have our x raised to the -2. And then inside, we're plugging in 4x to the 2/5. This negative means it's going down into the denominator. So we have 6 over 4x to the 2/5 squared. So that's going to give us 6 over 16x to the 4/5. And then we have a lot of simplifying going on right there. So 6 over 16 is just going to simplify to 3 over 8. But then we have x to the 4/5, which is the 5th root of x to the 4th power. And if you remember correctly, we're not allowed to have a radical in the denominator. So we have 4, we need 5. So we're going to multiply the top by the 5th root of x. So we have 3 5th root of x over 8x. And our domain is x cannot equal 0, because that would give us a denominator of 0. But the 5th root, that can be anything, so no big deal there. All right, so again, that was a very long video. That's because we had a lot to cover, but we're now done. So again, domain, it's a pretty important topic. Make sure you understand the basics, and then you can apply it to anything else. This is Longo, and I'm out. See you, bye.